Hi, I'm Austin Kaufman, and I'll be presenting my research on a model-free method for learning flexibility capacity of loads providing grid support. So at the high level in the power grid, one goal is to ensure that the power supply equals the power demand. And so the balancing authority is the group of individuals that are responsible for ensuring this balance. And to give an example, here is just a simplified geographical area to illustrate how a balancing authority might achieve this balance. So first it would take the gross demand and it would subtract this quantity from the renewable generation. This yields net demand, and then from this the balancing authority would schedule its controllable generators to track the net demand curve. Now, it may not be possible for the generators to fully track this curve due to their operating constraints, so there could be a residual between the net demand and controllable generation. So to ensure balance in the grid, the BA is going to require additional storage type services to track RBA. Now, it is well known that certain loads are inherently flexible and can operate as storage type services. And so to see this, imagine you have an ensemble of flexible loads whose baseline is given by the blue line. And so the baseline is the power consumption that the loads consume on any given day without helping the grid. And so suppose they were able to move their power consumption then to the red line. Now the difference between these two is what's termed the regulation signal, and it is also zero mean. So if the balancing authority chooses the altered consumption in an intelligent way, it can have it contribute to RBA so that these flexible loads can help balance power in the grid by deviating from their baseline in a zero mean fashion. So how much can flexible loads contribute to RBA? Well, that depends precisely on the capacity of the load. So, how much can they do really? And so there's many works on this, and one way in characterizing this capacity or figuring out what it is are what I call time domain characterizations. And so the aim of these works are essentially to take all the local quality of service constraints and just convert them to constraints on the regulation signal. So the idea is the quality of service at the loads dictates how the load can operate. And because of this is going to dictate in aggregate how much they can deviate from their baseline, and so how much they can contribute to RBA. And so once these constraints on the regulation signal are known, then the balancing authority could use this to plan regulation signals. Another approach is frequency domain characterizations. So in these, the idea is you take the local quality of service constraints and you convert them to constraints on the spectral density of the regulation signal and not the regulation signal. So the idea is how do I constrain in the frequency domain what type of spectral density the regulation signal can have? So there are various advantages to doing this, but you can look at the references linked prior for the reasons why. Now, in this setting, we have SBA, which is the spectral density of net demand, and this is the frequency domain analog of RBA. So now we're going to give it a little in more detail how this quantity SBA is computed just for concreteness. So imagine you have the same net demand data as you did before in the previous example. And so what we do next is the balancing authority would use this net demand data, so this would be past data, to estimate the spectral density, the empirical spectral density of this net demand. Could then fit a parametric model, so here it's an ARMA model, to this curve. And to figure out what SBA is, it could simply filter this parametric model. So the idea is anything that is not underneath the blue curve is then handled by other resources. So controllable generators, other classes of flexible loads, what have it. But the idea is that SBA is now the analog. So instead of RBA being the thing that the loads have to track, the balancing authority wants the loads power deviation to have spectral density SBA. And so we can see this here. The idea is that if SBA is what the balancing authority wants, so this is kind of the analog of RBA, then maybe the loads have some quality of service that dictates that, well, they can't get quite SBA, but they can get pretty close, and that's what this shaded region is. So really what the balancing authority wants to do in this method is figure out how big can that shaded region, or how much can I shade underneath the SBA curve. And so that helps, that's another characterization of capacity, and that's what we're going to talk about more in this talk. But the contribution is basically a model-free method to figure out how to get that shaded region. Now, in order to be able to do that, we have to distill our past work, which was a model-based method. So just denote the ensemble's power consumption as Y. Now, then the constraints that we've talked about, we enumerate them, and they're just inequalities. And each one of these signals is related to the power consumption through some linear system. And so a technical assumption is we need Y to be wide-sense stationary. And so the idea is with that, then the autocorrelation of Y and the spectral density are Fourier transform pairs. So now the idea is we want to take this constraint and put it in terms of the spectral density of the power deviation. And so in order to do that, there's two steps. The first step is you slightly relax this constraint. And so you take this and then you say probabilistically the probability of violating is small. So epsilon is a small number. Then you apply the Chebyshev inequality to get this bounded as a function of the variance. And from there, you can just simply apply the Weiner-Khinchin theorem because the mean of this random variable is 0. So we know that the variance is just the integral of the spectral density. And so here we have it. Not quite, but almost, is that we have this constraint on the spectral density implies some probabilistic guarantee about the original quality of service, which needs to be satisfied. And so what we want to do is we want to take this spectral density and convert it to 1 on the power deviation. And so the idea to do that is just a basic fact that if you have some spectral density S1, you can, this is a wide-sense stationary signal, you pass it through a linear system, you know what the output spectral density is. So just using this, we can convert that previous constraint to this, which is a constraint on the spectral density of the power consumption, implying some quality of service constraint. And so, what could Z1 be? Well, it could be the energy consumption of the flexible load. It could be the difference, so a rate constraint, or a state of charge. So anything that's related to the power consumption by a linear relationship. And so we could put all n of those constraints together to get our constraint set, which is a bunch of linear inequality constraints on the spectral density SY. And then we can use this to solve our, set up a problem that lets us figure out, okay, what is that shaded region? So we want to get really close to what the balancing authority wants, SBA, but we have to lie in the set that dictates the load's quality of service. So being in this set has some probabilistic guarantee that the load's quality of service will be met, which is important. So we definitely have to be in here, but we want to be close to what the balancing authority wants. And so now the idea is we want to extend our method to be model-free. So we want to be able to solve that optimization problem and get what we want without having to have a model of the flexible load. So we'll get into that a little more, but the idea to do this is we want to approximate our spectral density by a linear combination of spectral densities and weights. So these are our basis functions, but they're also spectral densities. And so the idea is our constraint set. This was what we had before. If we put it in our approximation, we get this. This is now a new set in terms of theta. Now this is highlighted in red because this is the model. So this is the information that dictates, like, okay, if you know the model, then you know this. So we want to be able to eventually not have to know what this is. And so you can see here that this is just an outer product. So we have a bunch of n linear inequality constraints on theta. And so we can do the same thing in the objective function, and we yield the following optimization problem. So we need a way to obtain this matrix B, where this is the model, without knowing what this is. And so to do this, let's just look at one element of this matrix. It's this integral of this function g and the basis functions. So the claim is that this thing can be estimated from simulation data. And so to see why, imagine you have a signal and it has this spectral density. It's the same thing as before. You can simulate, and what comes out of the simulator also has a certain spectral density. So the idea is that you can simulate, collect samples, use those samples to estimate this quantity at various frequency points, and then use this quantity to numerically integrate it at those frequency points to get that single element of the matrix B. You can then do that iteratively to get the whole matrix B. And the idea is we'll denote that as B hat, and all the other quantities as A hat, G hat, and C hat. And this sets up the same optimization problem just with the estimated quantities. So the idea is we want to apply our model-free method with the same SBA as in the model-based case and compare the results. And so here is just a zoomed-in version of the thing that the balancing authority wants, SBA. If we solve our method, the model-free case, this is what we get. And if we apply the model-based approach, we get the almost exact same thing, which is good. It shows that our model-free method is working just as well as the model-based method, but it requires less information. So just as a recap, a model-free method is developed to estimate the capacity of a collection of loads, and financial support is greatly appreciated from the NSF.